Hi 242. So we're going to talk about a new integration technique today. We've already talked about the method of substitution, and substitution was used to reverse the chain rule, but what we're going to do now is talk about a new technique, which is a technique that's going to reverse the product rule. And this new technique is called integration by parts, and it reverses the product rule. So let's first recall what the product rule is. Remember, this is a differentiation rule which is used in order to take the derivative of a product of expressions of x in this case. Right? So remember, our rule says we do something like derivative of the first times the second plus the first times derivative of the second. Right? Okay, so what we have here is the direction of taking the derivative, right? If I wanted to reverse that and use one of our techniques of the antiderivative, I would then say, well, I want to start with this expression on the right-hand side, and I want to say its antiderivative is, and I would say the stuff inside of the brackets here, right? That's the relationship between those two expressions. Okay. So if we want to make use of our notation that we have for the indefinite integral, we would write it as follows. We would write the antiderivative or indefinite integral of the stuff on the right side and that would equal the original starting function here. Okay. Well, that's great. As long as we're able to easily recognize that when we're given a function and it looks like this, that we actually exactly have this form. Now that might not be an easy thing to do simply because perhaps some algebra might have been done on this expression to actually simplify it first, or simplify it after the derivative had been taken, and so maybe it doesn't have its retained form that it looks like this. So not having a form that looks exactly like this because of algebra reasons could prevent us from being able to say that we exactly know what the antiderivative would be. So we would be a little bit stuck in that case. So what we do is we try to use a technique which is called integration by parts. And we could derive it from the product rule here. It's a little bit messy. Let's see if we can just work through it together quickly. We don't have to go into too much detail, but let's see. We start out with taking our rule for the product rule. Okay. And what I'm going to do is rearrange some of the terms. I'm going to keep all of the terms. I'm just going to move one to another side and just switch the two sides of the expression, just so that it looks in a certain way, so that what I do next is pretty clean. So rearranging, I get the following. That's this term over here. That's equal to this derivative minus this expression. Okay? So again, all I've done is rearrange the terms. I'm basically saying that this expression, which is this term here, right, is equal to this term minus this term. That's what this row here says, that line says. All right. Well, now that we have this rearranged in this way, what I can now do is say, okay, now I'm going to undo the derivative. So now let's go ahead and apply the antiderivative to both sides of this equation. But remember that the indefinite integral can be applied across a difference here. So what I could do is say I'm just going to apply the indefinite integral to all three parts of this line here. And so I have integral dx of that expression, integral that expression dx minus integral that expression dx. Okay? So what we now have is the following statement. That's an antiderivative. The antiderivative and the derivative are opposite operations. So if I'm taking the antiderivative of a derivative, they undo each other, so I'm left with just the inside expression. Okay? And hopefully you can see that. Well, in this way then, we've sort of broken this apart, and I see that I do have the original starting f of x, g of x expression there. I would just have to calculate two individual antiderivatives. Okay, well this is a little bit confusing as it's written, so what we do is we rename some of the parts with easy to remember letters so that we can remember them in terms of a nice little shorter string of letters. So let's make the following substitutions, not substitution to integrate, but just to rename parts. Okay, so this is the line we're currently working with. So let's do the following. So to clean it up, let's let f of x be u, and we'll let dv be g prime of x dx. Okay. What that means, just like when we did our U-substitution, is that when I have u equals f of x, that means that du is equal to f prime of x dx. And if I have dv is equal to g prime of x dx, well then v must be just equal to g of x. Okay. So what I can now do with those four declarations of parts is relabel everything that is happening in this line here. So when we do that, we get the following. Okay. This left side here is going to be the integral, let's see, f of x is u, g prime of x dx, that's dv. And now I have equals f of x, g of x, so that's u, v. Minus integral f prime of x, g of x, dx. Okay, well a little bit of reordering in that integral would show me that I have a couple of pieces here. G of x is just v. F prime of x dx is du. Right? So what that means is that this second antiderivative here is actually just v du. Okay? And this is the technique of integration by parts. Okay? And it's performed by saying, okay, I have some yucky expression in terms of x over here. I can then take that yucky integral and rewrite it as two parts. So take this undoable integral over here, take something that we don't know how to do, rewrite it as this piece minus another indefinite integral. And the entire goal of this technique is to take an integral here that we wouldn't be able to do by either substitution or standard techniques like just know the antiderivative, and rewrite it so that this antiderivative or indefinite integral is easier to do, right? That should be the entire goal of integration by parts, is that this integral is easier to do than this integral, right? It's a rewriting technique, okay? A note here to say is that just like with substitution and we were able to apply it to definite integrals, the integration by parts technique can also be applied to definite integrals. For example, if I had limits of integration on here in this integration by parts formula here, if I, for example, said go from A to B here, right, then what I need to do is simply remember that these two sides are equal. So if this is supposed to be the result of this integral, then I need to evaluate this entire right side also from A to B. So our notation where we say, if this goes from A to B, then I can go ahead and say, well, this piece needs to be evaluated from A to B, and this other integral over here will also need to be evaluated from A to B. Right? So if it's an indefinite integral and you don't have limits of integration, then you don't have to worry about doing this part over here, evaluating from A to B in each case. But if you do have a definite integral and you need to do it by integration by parts, the evaluate from A to B carries over to each of the two terms over here, right? You would evaluate this expression from A to B, and this integral would be done also from A to B. Okay, and we'll do an example of that tomorrow when we're all together in class. But let's go ahead and try an example here. We'll do an indefinite integral in this case instead of a definite integral. We'll leave that for tomorrow. Okay, so let's maybe move our integration by parts formula maybe to the top so we have enough room to work. Okay, so I'm going to do an indefinite integral, so integration by parts. Okay, so if I had integral u dv, that would be ub minus integral b du. Okay. And again, if it's a definite integral, apply the limits of integration across everywhere. Okay. So let's first try an example. And our first example is going to be the first matched problem in the textbook, which is the following. Okay. This is matched problem 1 from section 14.3 in your textbook. So notice here, if we were initially looking at this, we might think, maybe I should try a U-substitution. But notice that if I were to choose U as the exponent on E here, it has the same power as this one out here. So the U-substitution, if I chose this to be U, that's not going to help us here by canceling that X, right? If we were to, for example, do this, right? du is then equal to 2 dx, right? And so dx equals du over 2 here. And notice that when I do that, this is e to the u, but then that dx does not contain an x in it anywhere to cancel with that x, right? So a u substitution here is not going to work. So let's instead try integration by parts. Okay, so we've got choices, right? Because notice that if I start out with some sort of integral here, I have to make a choice. What is going to be the expression which is u, and what is the expression which is dv? I have to separate everything in this integral into either being u or dv. Okay. What we do need to do is remember that whatever we choose for dv, it has to contain the dx. There may be other stuff with it also, but it at least needs to have the dx. So we have a couple of options here in terms of choices. Okay, so our first option is that u could be x, and dv could be e to the 2x dx. So we could have this be u and this be dv. Okay. I'm hoping you can see that. Good. So let's call that option 1. U could be x, and dv could be e to the 2x dx. Or we could have option 2. Option 2 would say, well, or we could say that e to the 2x could be u, and this other stuff here could be dv. Okay? So that would say u is e to the 2x, and dv is equal to x dx. Okay? Now remember, the entire goal of integration by parts is that we take this integral that we don't know how to do, this, and we rewrite it where this new integral is easier to do than the one we started out with, right? So in each of these cases, what we're going to need to do is look to see if the integral v du is an easier integral to do than the one we're starting out with here, right? Well, to do that, what we need to do is have all 4 of the pieces, because notice that in this expression, I need to know u dv, I've already chosen those, but I need to know u v du in order to write the entire thing. Well, I currently only have, for either of the 2 options, u and dv, right? So let's get the rest of the parts for each option. So if u is equal to x, then that means that du is equal to dx. Okay? And if dv is equal to e to the 2x dx, then that means v, which is the antiderivative here, is just the antiderivative of e to the 2x, right? You can imagine sort of 2 little tiny antiderivatives going right here to undo that derivative notation there. Okay? So the antiderivative of this e to the 2x, that's one of the forms that we've talked about. That will be e to the 2x over 2. Okay? So what would the integral of v du look like in this case? Integral v du would be, well, here's v, and du is dx. And hopefully, that's an antiderivative we would know how to do. Again, remember the whole point is that this one is easier to do than this one. And that one appears to be something we would know how to do. So that's good. And that one's pretty easy. Just for comparison, let's see what this one would look like over here. So here's u. That would mean du would be, this requires chain rule, e to the 2x times 2 dx. And if this is dv, then v is equal to, remember, imagine in little tiny integral signs, they're undoing that derivative. Then v is going to be what? X squared over 2. I'm not worried about doing any plus c or anything over here when I do this yet, because I know that when I get to the end of this entire process, I'm going to put one big constant of integration at the end. Okay. So just to compare, let's see what integral v du would look like over here on this other option, on option 2. Okay. This would be what? The integral of v is x squared over 2, and du is e to the 2x times 2 dx. Okay, hopefully you can see that. Okay, it's not too blurry. Just a little bit. There we go. This is a yucky integral. We don't know how to do this one at this point. This would be really bad to do, right? So let's not even go with that option, especially since we have this nice option here in terms of option 1, okay? So these are going to be our choices for u, dv, du, and v here, so that we can now rewrite this integral using this ordered form, right? So here, if I'm making these choices and I have, which one was that? Option 1 or 2? Option 1 was the red one, right? Where u was equal to x and dv was this expression, right? So we're not using the blue. We're going to take away the blue. Taking away the blue. Because remember, option 1 was the red one. Okay, so this is u and dv here. So under that requirement where I have integral u dv, and there's my choices, this is equal to uv. Okay, so u is equal to x, v is equal to e to the 2x over 2 minus indefinite integral v, and we've already constructed this expression, but let's just make sure, e to the 2x over 2, and then du, which is dx. Okay, so again, see the form here. I have, this is integral of u dv is uv minus integral v du, right? And that's all the pieces here. Okay. Good? Okay. So now that we have that set, we're almost done, because this part is finished. That's a complete expression of x. There's no integral sign in that. We do have this indefinite integral over here to handle, but that one's straightforward because we know the antiderivative of e to the 2x, and this 2 in the bottom is just going to be a factor which could come out front. Okay, so when we're all done, we'll have something that looks like this. The first expression is x e to the 2x over 2 minus, what is this thing's antiderivative? This thing's antiderivative is e to the 2x over 2, but there's already a 2 down there, so they interact to make a 4. And let's not forget, these are indefinite integrals, so this is needing a constant of integration, a big C. Okay? And so this is our antiderivative of this indefinite integral. Right? So again, we take the derivative of this expression down here, and we get x e to the 2x. That's their relationship. Okay? So let's see how much time we're at. How about we just go with that example for today, for this video, and then for tomorrow, we'll do another example in class of an indefinite integral, and then we will do a definite integral example also. And then you'll get your next problem set. Okay? Hopefully you liked the video with me. Okay, see you tomorrow.